Hello, in this lecture we will find the area of a circle. In the drawing we have a circle, and inside the circle we have a shape, this shape, and two angles of this shape are right angles. Angle ADC equals to 90 degrees, and also angle BCD, this angle equals to 90 degrees also, and side AD of this shape equals to 4 units, while side DC of this shape equals to 6 units, and side BC of this shape equals to 8 units. And we want to find out the area of this circle. First of all, I will explain what is one-sided angles. What are one-sided angles? Actually, if we have two lines, line A and line B, we have two lines, line A and line B, and line C that intersects these two lines. Line C in the red color intersects line A at this point, while line C intersects line B at this point. Actually, angles alpha and beta are defined as one-sided interior angles. I write it down. Angles alpha and beta are defined as one-sided interior angles. Okay, angles alpha and beta are one-sided interior angles. And why are they called one-sided angles? The reason that they are called one-sided angles is because of the fact that they are located from one side of line C. They are actually located in the left side of line C. Both of them are located in the left side of line C. For that reason, they are defined as one-sided angles. And The second question is, why are angles alpha and beta are interior angles? Why angles alpha and beta are defined as interior angles? The answer to this question is because they are located inside the structure of lines A, C, and B. They are located inside this structure, therefore they are defined as interior angles. Okay, so actually that is the reason that they are called one-sided interior angles. And we have actually second type of one-sided angles. The second type is exterior one-sided angles. Actually, if we have line A and line B, okay, here are line A and line B, and the line C that intersects those two lines. Line C in the red color intersects line A at this point, while line C intersects line B at this point. Actually, here angles alpha and beta are defined as one-sided exterior angles. Okay, angles alpha and beta are defined as one-sided exterior angles. I will write it down. Angles alpha and beta are defined as one-sided exterior angles. Okay, angles alpha and beta are defined as one-sided exterior angles. Again, why are angles alpha and beta are one-sided angles? The answer to this question is very simple, because of the fact that they are located on the same side of line C. We have line C in the red color. They are located on the same side. Both of them are located on the same side of line C. That is to say, both of them are located on the left side of line C. For that reason, they are defined as one-sided angles. Okay, and again, the second question, why are angles alpha and beta are exterior angles? The answer is also very simple, because of the fact that angles alpha and beta are located outside this structure, outside of lines A, C, and B. They are located outside of this structure of lines A, B, and C. They are defined as exterior angles. Okay? In the next step, actually we have a new rule number 1, that relates to one-sided angles. Rule number 1 states that if the sum of the two one-sided angles equals to 180 degrees, then line A is parallel to line B. Okay, so I will read rule number 1 again. Rule number 1 states that if the sum of the two one-sided angles equals to 180 degrees, then line A is parallel to line B. Here we have angles alpha and beta that are defined as one-sided exterior angles, and if alpha plus beta the sum of those two one-sided exterior angles equals to 180 degrees, then according to rule number 1, line A is parallel to line B. Okay, if the sum of those two angles is equal to 180 degrees, then line A is parallel to line B. Again, if the sum of those two angles equals to 180 degrees, then we can deduce from it, according to rule number 1, that line A is parallel to line B. Those two lines, line A and B, are parallel to each other only if the sum of angles alpha and beta equals to 180 degrees. So that is the same rule also, that is for exterior one-sided angles, and the same rule applies also for one-sided interior angles. Those angles alpha and beta are defined as one-sided interior angles, and also here, if the sum of angles alpha plus beta equals to 180 degrees, then according to rule number 1, line A is parallel to line B. Line A is parallel to line B. Those two lines are parallel to each other. Okay, so rule number 1 applies to interior one-sided angles and also to exterior one-sided angles. Okay, so here I can add in brackets that it applies to interior and also exterior angles. interior or exterior. Okay, again, if the sum, rule number one states that if the sum of two one-sided angles of the if the sum of the two one-sided angles, and it doesn't matter if they are interior angles or exterior angles, if the sum of those two angles equals to 180 degrees, then line A is parallel to line B. Okay, so we actually can implement rule number one in our circle. Because actually it is given us in the question that angle ADC equals to 90 degrees. I'll write it down. Angle ADC equals to 90 degrees. And also angle BCD, this angle, also equals to 90 degrees. So the sum of them is 90 degrees plus 90 degrees is 180 degrees. And I will emphasize that those two angles are defined as one-sided internal angles. You can see it like this. And those two angles are one-sided internal angles. Okay? Because both of them are located in the left side of line segment DC, and you can view AD as line A, BC as line B, and DC as line C. Okay, so, and those two right angles are one-sided interior angles. Okay, I will write it down. And they are one-sided interior angles. Therefore, according to rule number one, rule number one states that if the sum of the two one-sided angles equals to 180 degrees, then line A is parallel to line B. So we have two one-sided angles, the sum of them equals to 180 degrees. So according to rule number one, line segment AD is parallel to line segment DC. Okay? So I'll read again the things that I want. Angle ADC equals to 90 degrees. This angle is 90 degrees. And angle BCD also equals to 90 degrees. This angle is 90 degrees, and the sum of those two angles, 90 degrees plus 90 degrees, is 180 degrees. And those two angles are one-sided interior angles. Again, you can see view AD as line A, BC as line B, and DC as line C. And therefore, those two angles are one-sided interior angles, and the sum of those two angles equals to 180 degrees. Therefore, according to rule number 1, line segment AD is parallel to line segment BC. Okay? The next step, we will connect together points A and C by a straight line. And we will also connect together points D and B by a straight line. And we will call to the intersection point between line segment AC and line segment DB O. Point O is the intersection point between line segment AC and line segment DB. Okay? And in the next step, I will explain you what are vertex angles. Okay? Actually, if you have two lines, line A and line B, we have line A and this is line A and line B that are intersecting each other. This is line B, and the intersection point is at this point. Actually, they create four angles. This is angle number 1. This is angle number 2. This is angle number 3. And this is angle number 4. Okay? So actually, in this drawing, we have two pairs of vertex angles. The first pair of vertex angles are angles 1 and 3, and the second pairs of vertex angles are angles 2 and 4. Okay, so actually I write it down. Angles 1 and 3 are defined as vertex angles, and according to a new rule, rule number 2, they are equal to each other. Okay, angle 1 equals to angle 3 according to rule number 2. So I'll read the things that I wrote. Angles 1 and 3 are defined as vertex angles. Those two angles are defined as vertex angles, and according to rule number 2, they are equal to each other. And we also have the second pair of vertex angles, and they are angles 2 and 4, and according to rule number 2, they are also equal to each other. So I write it down. Also angles 2 and 4 are also vertex angles, and angle 2 equals to angle 4 according to rule number 2. Okay, so I read the things that I wrote, and also angles 2 and 4 are defined as vertex angles, and according to rule number 2, they are equal to each other. That is to say, angle 2 also equals to angle 4. So those two angles in the red color, angles 2 and 4, are defined as vertex angles, and they are also equal to each other. Okay, so now we can write down rule number 4, rule number 2. Rule number 2 states that vertex angles are equal to each other. So I will read rule number 2 again. Rule number 2 states that vertex angles are equal to each other. So as I've already told you, we have two pairs of angles, angles 1 and 3 that are vertex angles and they are equal to each other, and also angles 2 and 4 are defined as vertex angles and they are equal to each other. So now I will draw them separately. The two pairs I will draw separately in order to emphasize the issue. If we have two lines, line A and line B, the first pair of vertex angles that are equal to each other So here angles alpha and beta are defined as vertex angles, and according to rule number 2 they are equal to each other, and the second pair of vertex angles that are also equal to each other so those are the second pair of vertex angles, and according to rule number 2 they are equal to each other, that is to say angle alpha equals to angle beta. Okay, so we actually can implement rule number 2 in our circle. Because we have those two vertex angles that are equal to each other. Actually, we have here also two pairs of vertex angles. Those are also two vertex angles that are equal to each other, but we relate only to those two angles that they are defined as vertex angles, and according to rule number 2 they are equal to each other. Okay, so we can write down that angle AOD and angle BOC are equal to each other because of the fact that they are equal and they are vertex angles, and according to rule number 2 vertex angles are equal to each other. Okay, so I write it down. Angle AOD, this angle equals to angle BOC, because they are vertex angles. Those two angles are vertex angles, and according to rule number 2 vertex angles are equal to each other. For that reason angle AOD equals to angle BOC. Those two angles are vertex angles, and according to rule number 2 they are equal to each other. So in the next step I will explain you what are alternating angles. Okay, actually if we have two lines, line A and line B, C that intersects those two lines. Okay. In the drawing you can see line A and line B, and line C that intersects line B at this point, and line C intersects line A at this point. Actually, here angles alpha and beta are defined as interior alternating angles. Again, angles alpha and beta are defined as interior alternating angles. I write it down. Angles alpha and beta are defined as interior alternating angles. Okay, angles alpha and beta are defined as interior alternating angles. And again, I will ask the same question as I asked about one-sided angles. Why are angles alpha and beta are defined as alternating angles? Why angles alpha and beta are defined as alternating angles? The answer to this question is very simple, because of the fact that angles alpha and beta are located on different sides in relation to line C. They are located on different sides of line C. They are defined as alternating angles. While angle alpha is located at the left side of line C, angle alpha is located at the left side of line C, angle beta is located in the right side of line C. Okay, they are located on different sides of line C. For that reason, they are defined as alternating angles. Okay, and I will ask the second question, that is, why are angles alpha and beta are defined interior angles? The answer will be the same as the answer for the one-sided angles, because of the fact that angles alpha and beta are inside the structure of lines B, C, and A. They are inside this structure. For that reason, they are defined interior angles. They are inside the structure of lines B, C, and A. For that reason, they are defined as interior angles. Okay, so those two angles, angle alpha and beta, are defined as interior alternating angles. Okay, and we also have the second type of alternating angles. If we have two lines, line A and line B, when you have line C that intersects those two lines A and B, again we have two lines, line A and line B, and line C intersects line B at this point, line C intersects line A at this point. Then angle alpha and beta are defined exterior alternating angles. Again, angles alpha and beta are defined as exterior alternating angles. I write it down. Angles alpha and beta are defined as exterior alternating angles. Okay, angles alpha and beta are defined as exterior alternating angles. Why are angles alpha and beta are defined as alternating angles? It is actually very simple because of the fact that angles alpha and beta are located at different sides in relation to line C. Actually, angle alpha located on the left side of line C, while angle beta is located on the right side of line C. So they are located on different sides of line C. For that reason, they are defined as alternating angles. And again, the second question is, why are angles alpha and beta are exterior angles? The answer is very simple, because of the fact that angles alpha and beta are outside of the structure of lines A, B, A, and C. They are outside of this structure. Okay, they are outside of structure lines B, A, and C. They are defined as exterior angles. Okay, and we actually have rule number 3 that relates to alternating angles. Rule number 3 states that alternating angles and when I mention alternating angles, it doesn't matter at all if they are interior alternating angles or exterior. It applies to both of them. Okay, I write it in brackets. It doesn't matter if they are interior or exterior. Alternating angles between parallel lines are equal to each other. So I will read rule number 3 again. Rule number 3 states that alternating angles, and it doesn't matter at all if they are interior or exterior, it applies to both of them. Alternating angles between parallel lines are equal to each other. So actually here we have here two interior alternating angles, and according to rule number 3, if line A is parallel to line B, line A is parallel to line B, then according to rule number 3, angle alpha equals to angle beta. Okay, again, if line A is parallel to line B, then angle alpha equals to angle beta. So, and it also applies the same according to rule number 3, of course, according to rule number 3, and the rule number 3 also applies to exterior alternating angles. Those two angles are exterior alternating angles, and if line A is parallel to line B, then according to rule number 3, angle alpha equals to angle beta. Okay, if line A is parallel to line B, if those two lines are parallel to each other, then angle alpha equals to angle beta. Okay, those are interior alternating angles, and it's also true for exterior, those are exterior alternating angles, and it's also true for interior alternating angles. If line A is parallel to line B, then angle alpha equals to angle beta. Okay, so in the next step we will relate to two triangles, triangle AOD in the green color, and triangle BOC also in the green color. Okay, we will relate to these two triangles. I will write it down. we will relate to triangle AOD and triangle BOC. On these two green triangles, we will prove that three angles of triangle BOC are equal to three angles in triangle AOD, and therefore those two triangles are similar to each other. Okay? So actually, as I've already explained you, angle AOD in triangle AOD equals to angle BOC in triangle BOC because of the fact that those two angles are vertex angles, and according to rule number 2, vertex angles are equal to each other. Okay, so I write it down. Angle AOD, this angle in triangle AOD, equals to angle BOC in the big green triangle because of the fact that those two angles are vertex angles, and according to rule number 2, vertex angles are equal to each other. So I add here so I read again the things that I wrote. We will relate to triangles AOD and BOC, those two green triangles. Triangle AOB equals to triangle BOC. Angle AOD equals to angle BOC. Those two angles, angle AOD equals to angle BOC, because of the fact that those two angles are vertex angles, and according to rule number 2, vertex angles are equal to each other. Okay, so that is the first angle that are equal to each other, that is equal to each other in those two green triangles. The second angle, actually this angle, angle DAO equals to angle PCO. So I write it down, angle DAO equals to angle PCO. Those two angles are defined as alternating angles, and they are located between parallel lines. Line segment AD is parallel to line segment BC. So because of the fact that we have two alternating angles that are located between parallel lines, between line segment AD and line segment BC that are parallel to each other, therefore according to rule number 3, they are equal to each other. Okay, so right here, because those two angles are alternating angles, And according to rule number 3, alternating angles, those two alternating angles between parallel lines, line segment AD is parallel to line segment BC, are equal to each other. Okay? So I read again the things that I want. Angle BC, angle DAO equals to angle BCO. Those two angles, angle DAO equals to angle BCO, are equal to each other because of the fact that they are alternating angles and they are located between parallel lines. Line segment AD is parallel to line segment BC, and therefore, according to rule number 3, they are equal to each other. Okay? And also, angle ADO, this angle is equal to angle CBO, to this angle. Okay? Why? Because those two angles are also alternating angles. Why? Because they are located on different sides of line segment BD. Okay? They are located on different sides of line segment TB, and they are located between parallel lines. Line segment AD is parallel to line segment BC. Therefore, according to rule number 3, they are equal to each other. Okay, so I write it down. Angle ADO equals to angle CBO because those two angles are alternating angles. And they are located between parallel lines. Those two alternating angles are located between parallel lines. Line segment AD is parallel to line segment BC. Therefore, according to rule number 3, they are equal to each other. Okay, we read again the things that I wrote. Angle ADO equals to angle CBO. Those two angles are equal to each other because they are alternating angles. They are alternating angles because they are located on different sides of line segment DB, and they are located between parallel lines. So line segment AD is parallel to line segment BC. Therefore, according to rule number 3, they are equal to each other. Okay, so we actually proved that three angles of this triangle are equal to three angles on this triangle, because we proved that angle BOC equals to angle AOD, and also we proved that those two angles are equal to each other, and we also proved that those two angles are also equal to each other. So we proved that three angles of this big triangle are equal to three angles of this green small triangle. Okay, so we actually proved that the two green triangles are similar to each other. Okay, so according to angle, triangle AOD is similar to triangle BOC. Okay. Okay, so according to A is the variation for angle. Triangle AOD is similar to triangle BOC. Those two plane triangles are similar to each other. And whenever we have two similar triangles, the following relationship exists between their sides. If the big triangle ABC is similar to the small triangle DEF, then the following relationship exists between their sides. Side AB over side DE. Okay, if these two triangles are similar to each other, then the following equality is true. AB over DE equals to BC over EF equals to AC over DF. Okay? Whenever we have two triangles that are similar to each other, then the following relationship exists between their sides. AB over DE equals to BC over EF equals to AC over DF. Okay? So we will use this equality in our two similar triangles. So because of the fact that those two triangles are similar to each other, we can write that OB over OD equals to OC over OA equals to BC over AD. Okay, OB over OD equals to OC over OA equals to BC over AD. OB over OD equals to OC over OA equals to BC over AD. But we know that BC equals to 8 units and AD equals to 4 units. So we can write here that BC equals to 8 units and AD equals to 4 units. Okay, we wrote that BC equals to 8 units and AD equals to 4 units. 8 over 4 is 2. Okay, so we actually have here two equalities. The first equality says that OB over OD equals to 2. So I will write it down separately. OB over OD equals to 2. You can multiply this equality by OD. OB so we got that OB equals to 2 times OD. Okay, OB equals 2 times OD. So if OD equals to A, then OB equals 2 times OD. So it equals to 2 times A. Okay. And we can also derive the second equality from this equality. We can write down that OC over OA equals to 2. Okay. Okay. OC over OA equals to 2. We can multiply this equality by OA and we will get that OC equals to 2 times OA. Okay, we got the second equality that states that OC equals 2 times OA. So actually if OC equals to B, if OA equals to B, OC equals 2 times OA, so OC equals 2B. Okay? OC equals 2 times OA. OC equals 2 times OA. If OA equals to B, OC equals 2B. Okay? In the next step, actually angle ADC equals to 90 degrees. It is given us in the question. Angle ADC equals to 90 degrees. again, angle ADC, this angle equals to 90 degrees. It is given us in the question. So if angle ADC is 90 degrees, then triangle ADC is a right triangle. And in any right triangle, we can implement the Pythagorean theorem that states that the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Okay, again, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So the square of the hypotenuse in the right triangle ADC equals to AC square. The square of the hypotenuse equals to the sum of the squares of the perpendiculars equals to AD square plus DC square. Okay, according to the Pythagorean theorem, in the right triangle ADC, AC square, that is the square of the hypotenuse, equals to the sum of the squares of the perpendiculars equals to AD square plus DC square. Okay? But what is the value of AC? The value of AC is actually the value of OA plus OC. OA plus OC equals to AC. But OA equals to B and OC equals to 2B. So OA plus OC equals to B plus 2B. B plus 2B equals to 3B. In total, we got that AC equals to 3B and AC square, AC equals to 3B and AC square equals to 3B square, while AD equals to 4. And AD square is 4 square. It is 16. And DC square. DC equals to 6, so DC square is 6 square. 6 square is 36. Okay, in total we got that 3B square equals to 16 plus 36. 16 plus 36 is 52. So we will get that 3B square equals to 52. Okay, 3B square equals to 52. Now we will take a root of this equation. We'll get that 3B equals to the root of 52. Okay, 3B equals to the root of 52, but 52 is 13 times 4, and we can split the root of 15 times 4 to 2 roots according to the rule that the root of A times B equals to the root of A times root B. Okay. Okay, so we got that 3B equals to the root of 4 times root 13. The root of 4 is 2, so I write it down. So we got that 3B equals to 2 times root 13. Now we divide this equality by 3 in order to get the value of B. So we got that so we divided by 3 this equality. We got that b equals to 2 over 3 times root 13. If b equals to 2 over 3 times root 13, that then the 2 times b equals to 4 over 3 times root 13. Okay, so I'll write here that b equals to 2 over 3 times root 13 while 2 times b equals to 4 over 3 times root 13. Okay, in the next step, actually we also know that angle BCD equals to 90 degrees. I write it down. Angle BCD equals to 90 degrees. So if angle BCD equals to 90 degrees, then triangle BCD is a right triangle. And in the right triangle BCD, we can implement the Pythagorean theorem in order to find out the value of A. Okay, according to the Pythagorean theorem, the square of the hypotenuse, that is to say dB square, equals to the sum of the squares of the perpendiculars, equals to BC square plus DC square. Okay, according to the Pythagorean theorem, in the right triangle BCD, the square of the hypotenuse, that is to say dB square, equals to the sum of the squares of the perpendiculars, equals to BC square plus DC square. Okay. What is the value of dB? The value of dB is actually dO plus OB. The value of dB is dO plus OB. But dO equals to A. And the value of dB, the value of dB is dO plus OB. But dO equals to A and OB equals to 2A. So the value of dB is A plus 2A. That is to say, the value of dB is 3B. The value of dB is A plus 2A equals to 3A. So the value of dB is 3A. And the dB square is 3A square. BC equals to 8 units. BC square is 8 square is 64. And DC equals to 6. And DC square is 6 square. That is 36. So in total we got that 3A square equals to 64 plus 36. 64 plus 36 is 100, so I write it down. So we got that 3 a square equals to 100. Now we will take a root out of this equality. We will get that 3a equals to the root of 100. The root of 100 is 10, so I write it down. So we got that 3a equals to 10. We divide this equality by 3 in order to get the value of a. So we got that a equals to 10 over 3 units, and if a equals to 10 over 3 units, then 2 times a equals to 20 over 3 units. So right here the values of a and 2a. A equals to 10 over 3 units. While 2a equals to 20 over 3 units. Okay, so in the next step I will copy this drawing to this page. Without a and b, I will only put the value of a and b in order to gain space on this drawing. Okay. OA equals to 2 over 3 times root 13. While OC equals to 4 over 3 times root 13. OB equals to 20 over 3 units, while OD equals to 10 over 3 units. Okay, so I copied this drawing to this page without A and B. I put only the values of A and B. So actually here we know all the values of all the line segments inside the circle. In the next step, we will extend line segment AC until it touches the circle at point P. Again, in the next step, we will extend line segment AC until it touches the circle at point P. Okay, we extended line segment AC until it touches the circle at point P. Point P is the point of contact between the circle and line segment AP, okay? So, actually, the new line segment CP is unknown. In order to find out the value of line segment CP, the new line segment CP, I will state new rule that will be rule number 4. According to rule number 4, if two chords are intersecting each other, for example, chord AB in the red color intersects with chord CD, at point O. Point O is the point of intersection between chord AB and chord CD. Okay, so if this is the reality, then the following equality is true. AO times BO AO times BO equals to CO times OD. Okay, I repeat again. If two chords are intersecting each other at point O, then the following equality is true. AO times BO equals to CO times DO. So I write rule number 4. I write it down. Rule number 4 states that if two chords that is to say chord AB and chord CB are intersecting each other at point O, again, point O is the point of intersection between chord AB and chord CD. Then the following equality is true. AO times BO equals to CO times DO. I will read rule number 4 again. According to rule number 4, if two chords, that is to say chord AB and chord CD, are intersecting each other at point O is the point of intersection between chord AB and chord CD, then the following equality is true, that AO times BO equals to CO times DO. Okay, AO times BO equals to CO times DO. Okay, so we actually can implement rule number 4 in our circle. Because we have chord AP that intersects with chord DB at point O. Again, chord AP intersects with chord DB at point O. Point O is the point of intersection between these two chords. Okay, so according to, so I write it down, chord AP intersects with chord DB at point O. Point O is the point of intersection between chord AP and DB. Therefore, according to rule number 4, AO times OP equals to DO times OB. I'll read again the things that I wrote. Chord AP intersects with chord DB at point O. Chord AP intersects with chord DB at point O. Point O is the point of intersection between chord AP and chord DB. Therefore, according to rule number 4, AO times OP equals to DO times OB. Therefore, according to rule number 4, AO times OP equals to DO times OB. Okay? So, AO equals to 2 over 3 times root 13. OP equals to OC plus CP. DO equals to 10 over 3 units, while OB equals to 20 over 3 units. So in total we got that 2 over 3 times root 13 times OP equals to OC plus CP, OP equals to OC plus CP, all equals to DO, that is 10 over 3, times OB, that is 20 over 3. Okay, what is the value of OC? The value of OC is 4 over 3 times root 13, so I will write it down. And CP is the unknown line segment, so I will leave it as it is. Here 10 times 20 is 200, so I write it down. Okay, in total we got that 2 over 3 times root 13 plus 4 over 3 times root 13 plus CP equals to 200 over 3 times 3. Actually we have 3 in the denominator of this side of the equation, and we have 3 in the denominator of the other side of the equation, so we can cancel 3. Okay, we cancel 3 here. So I will copy the equation after we divided it by 3. We cancel the 3. So in total, after we cancel the 3, what is left here is that 2 times root 13 times 4 over 3 times root 13 plus CP equals to 200 over 3. Here we can open the brackets. Actually 2 times 4 is 8, and root 13 times root 13 equals to 13. Root 13 times root 13 equals to 13, so I will write it down. So in total we got that 3 times 8 times 13 over 3 equals to plus 2 times root 13 equals to 200 over 3, because 10 times 4 is 8 and root 13 times root 13 is 13. Okay, 8 times 13 is 104, so I will write it down. In total we got that 104 over 3 plus 2 times root 13 times CP equals to 200 over 3. In this equality we subtract 104 over 3. Okay, from both sides of the equation. So we subtracted 104 over 3. So 104 over 3 minus 104 over 3 is 0. And what is left is only 2 times root 13 times CP here. And 203 minus 104 over 3 is what is left in this side of the equation. We'll take a common factor of 3 in the denominator, and we will get that 200 minus 104 equals to 96. 96 over 3. So again, we took a common factor 3 in the denominator, and 200 minus 104 is 96. In total, in the side of the equation we have 96 over 3. And here, what is left is 2 times root 13 times CP. 96 over 3 is 32, so I write it down. So we got that 2 times root 13 times CP equals to 32, because 96 over 3 is 32. Now we will divide this equation by 2. So 32 over 2 is 16, and here we divided this side by 2. We left with root 13 times CP. Now we will divide this equality by root 13, and we will get the value of CP. So we divided this equality by root 13, and we got that CP equals to 16 over root 13 units. Okay, so the value of CP, I will write it here. The value of CP is 16 over root 13 units. Okay. So in the next step, we will extend line segment DC until it touches the circle at point Q. Okay. Okay, we extend that line segment DC until it touches the circle at point Q. Point Q is the point of contact between the circle and chord DQ. Okay? The point of contact between chord DQ and the circle is point Q. Again, we created new line segment CQ, and we will calculate the value of line segment CQ according to the fourth rule. Okay, actually chord DQ intersects with chord AP at point C. Again, chord DQ intersects with chord AP at point C. Point C is the point of intersection of chord AP with chord DQ. Therefore, according to rule number 4, AC times CP equals to DC times CQ. So I'll read again the things that I wrote. Chord DQ intersects with chord AP at point C. Okay, chord DQ intersects with chord AP at point C. Point C is the point of intersection between chord AP and chord DQ. Therefore, according to rule number 4, AC times CP equals to DC times CQ. Okay, again, AC times CP equals to DC times CQ. C is the point of intersection between those two chords, okay? So, AC equals to 2 over 3 times root 13 plus 4 over 3 times root 13. So 2 over 3 times root 13 plus 4 over 3 times root 13 is 6 over 3 times root 13. So I write it down. And CP equals to, we've already found the value of CP. CP equals to 16 over 13 units. So 16 over root 13 units. All equals to DC. DC is 6 units times CQ is the line segment that is missing, and we want to find out the value of CQ. Okay, so I will leave CQ as it is. So in total we got that 6 over 3 times root 13 times 16 over root 13 equals to 6 times CQ. 6 over 3 is 2, and root 13, we have root 13 in the numerator and we have root 13 in the denominator. So we can cancel root 13. All equals to 6 CQ. So I write the new equality. So here root 13 is cancelled, so what is left is 6 over 2 is 2 times 16. So that is the only thing that is left in this side of the equation. In the other side of the equation we have 6 times CQ. 2 times 16 is 32, so I write it down. So in total we got that 6 CQ equals to 32. Now I will divide this equality by 6 in order to find out the value of CQ. CQ equals to 32 over 6. Okay, we got that CQ equals to 32 over 6. We can divide here this number by 2. Okay, we have okay, so we will get the CQ will be equal to 16 over 3 units. We divided here, we divided the numerator by 2, and we also divided by the denominator by 2, and we got that CQ equals to 16 over 3 units. Okay, so I write here that CQ equals to 16 over 3 units. Okay, in the next step we will extend line segment CB, this line segment, until it touches the circle at point R. Again, we extended line segment CB until it touches the circle at point R. Point R is the point of contact between the circle and chord BR, and we'll calculate the value of the new line segment RC according to the fourth rule. Actually, chord RB intersects with chord DQ at point C. Point C is the point of intersection between chord RB and chord DQ. Therefore, according to rule number 4, RC times BC equals to DC times CQ. So I will read again the things that I wrote. Chord RB intersects with chord DQ at point C. Okay, chord RB, this chord intersects with chord DQ at point C. Point C is the point of intersection between chord RB and chord DQ. Therefore, according to rule number 4, RC times BC equals to DC times CQ. According to rule number 4, RC times CB equals to DC times CQ. Again, RC times CB equals to DC times CQ. Okay? RC is the missing variable, so I will leave it as it is. RC times BC equals to 8 units, equals to DC equals to 6 units, times CQ equals to 16 over 3 units. So, in total, we got that RC times 8 equals to 6 times 16 over 3. Okay, so 6 over 3 is 2, so I write it down. So we got that 8 times RC equals to 2 times 16. 2 times 16 is 32, so I will write it down. So in total we got that 8 times RC equals to 32. We'll divide this equality by 8. 32 over 8 is 4. So we'll get that RC equals to 4 units. Okay. We found out that the value of RC is 4 units. So I write here RC equals to 4 units. Okay, so actually we have all the values of all the line segments inside this circle, and the only missing thing is the radius of this circle. In order to find the radius of this circle, I will state a new rule, rule number 5. According to rule number 5, if two chords are intersecting each other at 90 degrees, if chord AB intersects at chord CD at 90 degrees, so at the point of intersection, we'll name this point, the point of intersection, point O. So at the point of intersection, the two chords A, B and CD create between them 90 degrees. Actually all the angles at point O, all the 4 angles equal to 90 degrees. So if this is the reality that we have two chords that are intersecting each other at 90 degrees at point O, then the following equality is true. That 4 times r squared, when r is the radius of this circle, equals to AO squared plus BO squared plus CO squared plus DO squared. Okay? 4 times the radius of this circle square equals to AO square plus BO square plus CO square plus DO square. Okay, so I write rule number 5. I write down rule number 5. Rule number 5 states that if two chords are intersecting each other at 90 degrees, and the point of intersection is point O, at point O, so I will add here that if two chords, in brackets I will add that they are actually chord AB and chord CD. Then the following equality is true. That 4 times R square equals to AO square plus BO square plus CO square plus DO square. So I will read rule number 5 again. Rule number 5 states that if two chords are if two chords, that is to say chord AB and chord CD, are intersecting each other at 90 degrees, they create between them at the point of intersection 90 degrees. At point O, the point of intersection is point O. Then the following equality is true, that 4 times R square, when R is the radius of the circle, equals to AO square plus OB square plus CO square plus DO square. Okay, so we actually can implement rule number 5 in our circle. Because first of all, angle BCD, this angle equals to 90 degrees. Angle BCD equals to 90 degrees, and actually all the 4 angles at point C are equals to 90 degrees. Okay, so actually chord RB intersects, this chord RB intersects with chord DQ at 90 degrees. I write it down, chord RB intersects with chord DQ at 90 degrees. At this point, all the angles at the point of intersection, all the angles equal to 90 degrees. At 90 degrees at point C. Point C is the point of intersection between chord RB and chord DQ. So whenever you have two chords that are intersecting each other at 90 degrees, you can implement rule number 5 on that circle. So we have in this circle two chords, chord RB and chord DQ, that are intersecting each other at 90 degrees. Therefore, we can automatically operate rule number 5 on this circle. So according to rule number 5, 4 times the radius of this circle square, the radius of the circle squared equals to RC squared plus BC squared plus DC squared plus CQ squared. So I'll read again the things that I wrote. Angle BCD equals to 90 degrees. This angle is a right angle. It is given us in the question. It equals to 90 degrees. So actually all the angles here, all the 4 angles are right angles. Chord RB intersects with chord DQ at 90 degrees. Chord RB intersects with chord DQ at 90 degrees. All the angles in point C are 90 degrees, right angles. So according to rule number 5, so we can implement whenever we have two chords that are intersecting each other at 90 degrees, we can implement rule number 5. So according to rule number 5, 4 times the radius square equals to RC square plus BC square plus DC square plus CQ square. 4 times the radius of this circle squared equals to RC square plus BC square plus DC square plus CQ square. Okay, so 4 times the radius of the circle squared equals to RC squared. RC equals to 4, so RC 4 square is RC square is 4 square. 4 square is 16 plus BC square. BC equals to 8, so BC square is 8 square, and 8 square is 64 plus DC square. DC equals to 6, so DC square is 36 plus CQ square. CQ is 16 over 3, and 16 over 3 is 5/3, and 5/3 squared is 28.444. So in total we got that 4 times the radius of the circle squared equals to 16 plus 64 plus 36 plus 28.444. Now 64 plus 36 is 100. 100 plus 16 is 116, and 116 plus 28.444 equals to 144.444. So I'll write it down. So we got that 4 times the radius squared equals to 144.444. We'll divide this equality by 4 in order to get the radius squared. So we got that the radius squared equals to 36.111. Okay, so and the area of any circle A equals to pi times the radius of the circle squared. The formula for the area of any circle equals to pi times the radius of the circle squared. We know that the radius squared equals to 36.111, so we'll multiply 36.111 by pi in order to get the area of the circle. So the area of our circle equals to pi times r squared. Pi times r squared, and r squared equals to 36.111. So we will multiply pi by 36.111. So we actually got that the area of the circle equals to pi times 36.111, or in terms of numbers we can write that the area of the circle it is 36 pi times 36.111 square units, or the area of the circle in terms of numbers equals to 113.45 square units. Okay, the area of the circle equals to 113.45 square units. The area of the circle equals to 113.45 square units. Okay, so now I'll summarize the lecture. Actually, we wanted to find out the value of this circle, and inside the circle we have a shape, and two angles inside the shape are right angles. They are equal to 90 degrees. Side AD equals to 4 units, side DC of the circle equals to 6 units, side BC equals to 8 units, and we want to find out the area of this circle. Okay, in order to find out the area of this circle, we must define a couple of terms. The first term that we defined are one-sided angles. Okay, so what are one-sided angles? Okay, one-sided angles are two angles between two lines and third line that intersects those two lines, and actually they are located on the same side of the third line. Okay, I'll show you the drawing of those angles, otherwise it will be very difficult to understand what I'm talking about. So actually what are one-sided angles? If we have two lines, line A and line B, and the third line, line C, that intersects those two lines at those points, those are the points of intersection between line C and line A and B, then actually those two angles, alpha and beta, are defined as one-sided interior angles. Why they are defined one-sided angles? Because of the fact that they are both located on the same side of line C. Both of them are located on the right side of line C. For that reason they are one-sided angles. And why are they interior angles? Because they are actually inside the structure of lines A, C and B. Okay, so those two angles are one-sided interior angles, while those two angles are one-sided exterior angles. Okay, they are exterior angles because they are located outside the structure of lines A, C and B. Okay, and they are actually one-sided angles because both of them are located in the right side, on the left side of on the right side of line C. Both of them are located on the right side of line C, the red line. For that reason, they are defined as one-sided angles. And we have rule number 1 that states that if the sum of the two one-sided angles, and it doesn't matter if they are interior or exterior angles, equals to 180 degrees, then line A is parallel to line B. So if the sum of those two angles, alpha and beta, equals to 180 degrees, then line A is parallel to line B. Okay, and also here, if the sum of those two angles is 180 degrees, then according to rule number 1, line A is parallel to line B. Okay, so we actually implemented rule number 1 in our circle because we have here two one-sided angles. This angle equals to 90 degrees and this angle also equals to 90 degrees, and they are one-sided angles because they are located at the same side of line segment DC. And the sum of those two angles equal to 180 degrees, because 90 degrees plus 90 degrees is 180 degrees. So we have two one-sided angles that the sum of them equals to 180 degrees. So according to rule number 1, line segment AD is parallel to line segment BC. Okay. then we define the theorem of vertex angles. If we have two angles that are intersecting each other, and this is the point of intersection between line A and line B. If we have two lines that are intersecting each other, and this is the point of intersection, they create four angles: 1, 2, 3, and 4. And actually, angles 1 and 3 are defined as vertex angles, and they are equal to each other according to rule number 2, and also angles 2 and 4 in the red color are defined as vertex angles, and according to rule number 2 they are also equal to each other. So actually we have rule number 2 that states that vertex angles are equal to each other. So here angles alpha and beta are defined as vertex angles, and according to rule number 2 they are equal to each other, alpha equals to beta. And also here we have two vertex angles, and according to rule number 2 they are equal to each other, that is to say alpha equals to beta. Okay, so actually we can say that angle AOD and angle BOC are vertex angles, those two angles, and according to rule number 2 they are equal to each other. Okay, and then we defined the theorem of alternating angles. If we have two lines, line A and line B, line A and line B, and line C that intersects those two lines, this is the point of intersection between line C and line B, and this is the point of intersection between line C and line A. Actually, angles alpha and beta are defined as alternating angles because they are located on different sides of line C. Okay, while angle alpha is located in the right side of line C, angle beta is located on the left side of line C. For that reason they are defined as alternating angles, and they are also interior angles because they are inside the structure, both of them inside the structure of lines A, B, and C, inside this structure. And we have also the same type of angles that are alternating angles. These angles are exterior alternating angles, and because of the fact that they are exterior angles, because of the fact that they are located outside of the structure of lines A, B, and C, and they are alternating angles because they are located at different sides of line C, while angle alpha is located on the right side of line C, angle beta is located on the left side of line C. For that reason they are defined as alternating angles, and they are outside of this structure of lines. For that reason they are exterior angles. So those are the exterior alternating angles, and we have rule number 3 that states that alternating angles, it doesn't matter if they are interior or exterior, between parallel lines are equal to each other. So actually, if we know that line A is parallel to line B, if line A is parallel to line B, then angle alpha equals to angle beta, and also here, if line A is parallel to line B, then angle alpha equals to angle beta, according to rule number 3 that states that alternating angle between parallel lines are equal to each other. Okay, so we implemented this rule in our circle. First of all, as I've already mentioned, those two angles are equal to each other because they are vertex angles, and according to rule number 2, the vertex angles are equal to each other. And also we have these two angles that are also equal to each other because of the fact that they are alternating angles between parallel lines. Line segment AD is parallel to line segment BC, and according to rule number 3, alternating angles between parallel lines are equal to each other. Okay, and also those two angles are alternating angles, and they are located between parallel lines. Line segment AD is parallel to line segment BC, and therefore, according to rule number 3 that states that alternating angles between parallel lines are equal to each other, they are equal to each other because they are located between parallel lines, parallel line segments. Line segment AD is parallel to line segment BC. So we actually proved that 3 angles of this right triangle are equal to 3 angles of this right triangle. Therefore, we proved that those two right triangles are similar to each other, and therefore, whenever you have a similarity between two triangles, you have the following relationship between the sides of those triangles. If triangle ABC is similar to triangle DEF, then AB over DE equals to BC over EF equals to AC over DF. So we implemented this equality in our circle, in our two similar triangles, because we know that those two, we already proved that those two great triangles are similar to each other. So according to the equality that I stated here, we can say that OB over OD equals to OC over OA, that equals to DC over, that equals to BC over AD. Again, OB over OD equals to OC over OA, and it equals to BC over AD. We know that BC equals to 8 units and AD equals to 4 units. So 8 over 4 is 2. So we got those two equalities, that OB over OD is 2, and also OC over OA is 2. And we got from these equalities that OB equals to 2 times OD and OC equals to 2 times OA. Okay, so if OA equals to B, then OC equals to 2B, and according to the equality that we found, and if OD equals to A, then OB equals 2 times A. Okay, and then in order to find out the value of A, actually we know that angle ADC is a right angle, so triangle ADC is a right triangle, so we can implement the Pythagorean theorem in order to find out the value of B. According to the Pythagorean theorem, the square of the hypotenuse, that is to say AC square, equals to the sum of the squares of the perpendiculars, equals to AD square plus DC square. Okay, in the right triangle ADC, AC square equals to AD square plus DC square, and the only missing variable is AC that equals to 3B, so we put all the data in this equality, and we found out that the value of B is 2 over 3 times root 13, while 2 times B equals to 4 over 3 times root 13 units. Okay, and then we also know that angle BCD equals to 90 degrees, therefore triangle BCD is a right triangle, and again we can implement the Pythagorean theorem in the right triangle BCD. According to the Pythagorean theorem, the square of the hypotenuse, that is to say dB square, equals to the sum of the squares of the perpendiculars, equals to BC square plus DC square. Okay, according to the Pythagorean theorem, dB square equals to BC square plus DC square in the right triangle BCD. And again, we know that dB equals to 3A, BC equals to 8 units, and DC equals to 6 units. The only missing variable is A, so we easily solve the equation of the Pythagorean theorem in order to find out the value of A and 2A. So we found out that DO equals to A, that is 10 over 3, and OB equals to 2 times A, that is 20 over 3. So we actually found out the values of all the line segments in this inside the circle, and then we actually extended line segment AC until it touches the circle at point P. And in order to find out the value of line segment CP, we implemented the rule number 4. Actually, rule number 4 states that if two chords, that is to say chord AB and chord CD, are intersecting each other at point O, then the following equality is true, that is AO times BO equals to CO times DO. Okay, so we can implement rule number 4 in our circle, because we have chord AP that intersects with chord DB. Point O is the point of intersection between those two chords. So according to rule number 4, AO times OP equals to DO times OB. Okay, AO times OP equals to DO times OB. But we know the values of all the line segments here, so we put the data inside the equality, and we found out that CP equals to 16 over 13 root 13 units. Okay, we found out the value of CP that is equals to 16 over root 13 units, and then we extended line segment DC until it touches the circle at point Q. Okay, and then in order to find out the value of line segment CQ, we implemented rule number 4 in our circle, because we have chord DQ that intersects with chord AP at point C. Okay, so according to rule number 4, AC times CP equals to DC times CQ. Okay, according to rule number 4, AC times CP equals to DC times CQ. Again, we have all the values of all the line segments. So we put the data inside the equality, and found out that CQ equals to 16 over 3 units. Okay, and then we extended line segment PC until it touches the circle at point R. Point R is the point of contact between the circle and chord RB. So again we implemented rule number 4 in order to find out the value of RC. Chord RB intersects with chord DQ at point C, so according to rule number 4, RC times C, RC times BC equals to DC times CQ. Okay, RC times BC equals to DC times CQ. Okay, and here the only missing variable is RC in this equation, so we found out that the value of RC is 4 units. Okay, and now we have all the values of all the line segments inside the circle, and the only missing thing is the radius, and in order to find out the radius of this circle we implemented rule number 5. And actually, according to rule number 5, if two chords, that is to say chord AB and chord CD, are intersecting each other at 90 degrees at point O, point O is the point of intersection between chord AB and chord CD, then the following equality is true, that 4 times the radius of this circle squared equals to AO square plus BO square plus CO square plus DO square. Okay, so we can implement rule number 5 in our circle, because we know that this angle BCD equals to 90 degrees, and actually chord RB intersects with chord DQ at 90 degrees at point C. So according to rule number 5, 4 times the radius of this circle squared equals to RC square plus BC square plus DC square plus CQ square. Okay, according to rule number 5, 4 times the radius of the circle squared equals to RC square plus BC square plus DC square plus CQ square. And again, the only missing variable is R. We know all the values of all the line segments here. We put the data inside this equality, and we found out that the radius of the circle squared equals to 36.111. And the area of any circle is pi times the radius of the circle squared, and we have the value of R squared, so the area of the circle equals to pi times R squared, and we know the value of R squared equals to 36.111, so the area of this circle will be equal to pi times R squared, and R squared is 36.111, or the area of this circle equals to pi times 36.111 square units, or in terms of numbers, the area of this circle equals to 113.45 square units. Again, the area of this circle equals to 113.45 square units. Okay, thank you very much.